right, so this last lesson is on finding the average rate of change of a polar function. And you already know how to do pretty much everything in this lesson. So we're going to review some things that we haven't done in a while. One of them we haven't done since Unit 4, but we've done the average rate of change quite a bit throughout the whole year. So whenever we're finding the average rate of change of any function, the numerator, the intervals from A to B, the numerator you could do f of b minus f of a, and the denominator you do b minus a, and it gives you the rate at which, in this case, the rate at which the radius is changing per radian. So let's look at the first one. For example 1, we're going to consider the graph of the polar function r equals f of theta, where f of theta is 3 minus 3 cosine of theta in the polar coordinate system. What is the average rate of change of r, which is f of theta, over the interval from pi over 2 to pi? So I'm going to, even though we're going to do this in the calculator, I do want you to write out what we're doing. This is not going to be on the free response question. The polar average rate of change is not, but the actual average rate of change is for other types of functions. So I just want to practice writing it so you get all the points you can get. Okay, grab a calculator if you don't have one. All right, so what we're going to do is f of pi minus f of pi over 2 over pi minus pi over 2. It's kind of messy. And I cannot promise you that the average rate of change questions on the AP test are going to be on the calculator version. I just don't know. We are going to practice it like they are. I know you can plug these values in. We've plugged them in so much. I know you can do it. So we're going to do it in the calculator today. All right, so you need to make sure whatever calculator you have is in polar mode. It's possible that someone else, if you're using a yellow one, someone might have changed it back to function mode, my other classes. So let's make sure we're in polar mode. And then we are going to go to y equals, y'all good? Okay. We're going to go to y equals, which is going to show up as r equals if you're in polar mode. Oops, I did 33. Let's not do 3. All right. And when you're in polar mode, if you hit the X button, it shows up as theta, because X is only for function mode. All right. Then we're going to go back to the home screen, and we're going to get the fraction. So alpha y equals, and then hit enter on 1. And then we're going to go to where we used to go to get y1, but it's now going to be r1. Do you guys remember where we used to go to get y1?
Alpha trace.
Absolutely. So we're going to do alpha trace, and r's are going to show up, and we just type that in r1. And so where we have f of pi, we're going to do r1 of pi. So in parentheses, we'll put the pi. And then again, it's alpha trace. Choose r1. And then in parentheses, put pi over 2. I think my battery in my mouse is dying. All right, you guys can go ahead in the denominator. I'm having issues. In the denominator, do pi minus pi over 2. So several times throughout the year, oh, sorry, just kidding. We're going to just run around this one we're going to be accurate to 3 decimal places, which means we can round it or we can truncate it. So if you decide to round it, it is going to be 1.910. If you decide to truncate it, it's going to be 1.909. Or you could just go to 4 places and then you're absolutely right no matter what, rounding or truncating. Did y'all get that? It's a calculator miracle if you did. Okay. Let's look at the next one. Now, these are kind of difficult to do whenever they give you the graph because the polar coordinate system is so different from the rectangular coordinate system. If this was a rectangular coordinate system and they were asking you which intervals is the average rate of change going to be 0, then you would just look for an interval where you got a horizontal line. Well, that is not going to work for this because it looks like when you go from here to here, the R is 3 and then the R is 3 again. So that's no change. But also, when you go from here to here, the R is 3 and the R is 3. So something's up because they all can't be the answer. There's only one right answer. And so what's happening is sometimes the R is -3 and sometimes it's +3. So I think the best way to do this problem is to not look at the graph and just look at the function and figure it out that way. So we're going to divide up the work. So we're going to let's just have Jonathan's row test out A. I'm going to abbreviate. All right. And then we'll have Elsie and Derek's row test out B. And then we'll have everybody else test out C. And then I'll do D. Sorry, if you're not sure what row you're in, it might help you, it might not. All right, so what you're going to do first is put the function into the calculator in R equals. And we'll get our fraction and then just use your points for whichever one you're using. Jonathan's row is that one. That's you. All right, so I did not get 0. All right, those of you that did A, did y'all get 0? Those of you that did B, did y'all get 0? What about my C people? Yes, it is C. C is the only one where the average rate of change is 0. So it looks like those other intervals, like it's changing from 3 to -3, from -3 to 3. So it's hard. The graph gets confusing. Now I know I can't count on that graph because we've graphed these flowers before, or roses I should say, and this one graphs in this direction. So I know, like in this case, I'm plugging in 3 pi/4, but I'm getting -3. So I know that one is a weird one just because of the way it's graphed. This Lemachon, is actually a cardioid. It that kind of weird stuff doesn't happen. Like it just goes in order. So this one, it tells you that in this polar system of the domain from 0 to 2 pi, there's no holes, and the graph passes through each point exactly once. The other one, the graph passed through the point 0, 0, where r is 0, like 4 times. So this is a totally different situation. And it passes through the label points A, B, C, D in that order. And so I know I have, this is all that's going on. Woo. So in this case, my R is positive everywhere because when I plug in 0, I'm going to get this positive whatever this number is. When I plug in pi over 6, I get this. I'm not 100. I think when I plug in pi over 2, I get 0. When I plug in pi, I get here. So it's always positive all the way around. So we can use this graph to answer questions about how R is changing because R is always going to be positive in here. Okay, so if I'm going to figure out which one of these has the average rate of change that is the least, if I go from A to B, I'm looking at how R has changed. So if I go from A to B, did my R change at all? It's on the same circle. So R doesn't change. So if R doesn't change, what would you say the average rate of change is? No change, it's 0. All right. And if we're looking at from B to C, here is our B. It looks like it's on a circle. If we're going by twos, it's probably like 3 to here, which is between 4 and 6, so a little bit more than 5. So R is increasing in this case. I don't know exactly how much is increasing, but I know because R is increasing, the average rate of change is going to be positive. And that's really all I need to know to answer this question in a second. All right, what about how is R changing from C to D? So if I could change at all, or it's the same circle? It's the same. So R doesn't change. So the average rate of change is 0 again. Great. And then from D to A, so here to here, is the R getting smaller or bigger? Smaller. From D to A, smaller. R is decreasing. So what does that mean about the average rate of change? It's negative. So if we ever set, it's a lot to remember, but if you ever say the average rate of change is decreasing, it means the graph is concave down. We'll review all that stuff. So which one of these should be the least? A negative number, a positive number, or 0 would be the least? Yeah, negative. All right. The last thing we're learning today is using the average rate of change to estimate a value. This is a really big concept we do in calculus. It's called local linearization. We're not going to call it that here, and yours says something different than mine. Yours says y equals y1 plus m. You don't need to rewrite it because it's already on your paper. Sorry, I meant to change that out. This is a formula that we learned about in Unit 4. Does it look familiar at all to you? We've learned a lot since then. Okay, I'm going to pull it back up just to prove to you. I had to prove it to myself too, because typically in pre-calculus, we don't learn this, but we did learn this. I don't know the date, but right here are my notes. And right here it is. So we used the rate of change to find the equation of the line that goes through a certain point. So we found the slope using the old slope formula, like from Algebra 1. And then we used a point on the line to write the equation. So we're going to do the same thing with polar. And then one thing we're going to do that I didn't look at all the notes. I don't think we did this back then in 0.043, we're going to use that equation to approximate another value on the function. All right, so what we're going to do is use the average rate of change in the place of the slope. So for m, that's going to be our average rate of change. And then we could use either point to write our function we use to approximate. All right, so on example 4, let's start off just by finding that average rate of change. I'm going to say it's m for the slope. Okay. And then don't forget, in the numerator, that's where you subtract the y values or the f of theta values. I shouldn't say y. In this case, there are values. And you have options. You can do -1 minus 2, or you can do 2 minus -1, up to you. But after you make that decision, your denominator has to follow suit. So if we do -1 minus 2, in the denominator we have to do 7 pi over 6 minus pi over 6. Okay, we're going to let our calculator figure this out for us. Now we don't have a function to plug into R. That's okay, we'll just do the little fraction guy. I want you guys to all do this because there's something else I'm going to show you how to do after we type it in. Okay, so one thing I want you guys to remember when you're doing the calculator portion of your AP test is that you only round once. So it's like YOLO, but with round instead of living. So I'm going to write out this whole decimal. This actually came up today in my calculus class that they were doing something and they rounded too soon and it made their answer wrong. Your answer has to be right to 3 decimal places. If you round early, it messes you up. So what we're going to do to keep from having to type all this out, we're going to store this in the calculator. All right, and to store in the calculator, you hit the store button that is right beside the 1. So the last thing that was typed in there, the answer, is going to get stored. And I'm going to go ahead and call it m. So to get to m, it looks like it's going to be alpha and then the division symbol. And then enter. Now, I really don't think there's going to be any kind of polar graphs on your free response. There will be average rate of change on there. Don't think it's going to be polar. But if by chance there was a situation where you stored something in your calculator and you wrote where they're grading that's m, you don't have to keep writing that decimal. You can just write m. When you're showing your work, you can just write m. That's what we're going to do when we do this. Sometimes you're running out of time and you don't have time to do write every little thing out. But if you tell them m is this number, when you're showing your work, just call it m. So we're going to say that r, we're using this guy. Oh, hold on. Let's write it down. So instead of y and x, let's change it to r and theta. And that is not right. Hold on just a second. That's supposed to be r. So r is going to be equal to r1, which is r from one of your points, times m plus m, times theta minus theta 1. All right, which point do you guys want to use? We have options. We can use these two or these two. The first two, okay. And so this is going to be R1 and this is going to be theta 1. So it's going to be 2 plus, I'm just going to say m. This first theta is the variable theta. So it's going to be in your problem minus pi over 6. Okay. Now in calculus, we call that the tangent line. And we're doing either tangent line approximation in a second or local linearization approximation, and it means the same thing. So what we're going to do is we're going to use that equation to approximate f of 5 pi over 6. So in the place of theta, we're going to put that 5 pi over 6. All right, and then I'm just going to type that in my calculator just like it looks. Not the stuff that's on the left, just the stuff that's on the right. Maybe. There we go. We got 0. So that's an approximation for f of 5 pi over 6. It's fine. So is it like e negative something? Yeah, you're fine. It's just a little bit of a glitch in the calculator, but that always means 0. So any number and then e, I would say if it's negative 6 or below, it's definitely good. Maybe negative 5 or below. All right. Any other questions?